This video will go over section 5.2, which is on balancing chemical equations. And this time we'll focus on balancing chemical equations that are involving ionic compound with polyatomic ions. So when you encounter polyatomic ions, you will always want to keep them as one unit, one ion. You do not want to split the atoms, and you want to keep them as one formula, as one ion. And so, for example, here we have a picture of two clear solutions being mixed. The one on top is the MgCl2 aqueous solution, and the one on the bottom is the Na3PO4 aqueous solution. And you see then that when you mix them, it produces a white cloud, which is what we call a precipitate. So this represents a precipitation reaction. In a precipitation reaction, you're producing a solid. So the top solution has the magnesium and chloride ions, which are monoatomic ions. And the bottom solution has the sodium and the phosphate ion. And the phosphate here is a polyatomic ion. And you can see in the model that it's made of one phosphate surrounded by 4 oxygen atoms. And you see how in the lower left bubble you have the blue sphere surrounded by 4 red spheres, and these represent the, the phosphorus in blue and the oxygens in red. And so they stay as like that. They don't dissociate, they don't break apart. They stay as this unit, which is an ion with 3 negative charges for phosphate. And so the phosphate will mingle with the magnesium when you mix the two solutions together, and you see that on the left side, on the right side, now the phosphate are with the magnesium. Magnesium is in gray, it's a gray sphere here. And this time they look like they are packed together in a regular pattern. So that suggests a solid. And so indeed the physical state of Mg3PO4 2 times is S for solid. And that's the precipitate. We are forming a precipitate here. And then the other ions, the Na plus and Cl minus, are just floating around in solution. These are forming a NaCl, which is a soluble compound. So it stays as, single ions floating in water. So to balance this skeletal equation, because what we see here is the skeletal equation, it's not balanced yet. So to balance, you want to first count the number of ions you have on both sides. And as I said, it's ions. So you will count the Na plus ions. On the on the left side, you have 3 Na in the sodium phosphate compound, and 1 Na on the right in the NaCl compound. Then you count the phosphate ion. You count, per ion. So you count the phosphate, and you don't count each P and each O. You count it as PO4. You count that unit, and you find it that there is 1 on the left side, and there is 2 on the right side. It's easy to see because it's surrounded by parentheses, and the 2 here applies to 2 phosphate. Next, you can count the number of magnesium ions. There is 1 on the left, 3 on the right. And the chloride ions, there is 2 on the left, 1 on the right. So when you're ready to balance, you want to start with polyatomic ions, always. When you have polyatomic ions in your equation, always start by the polyatomic ions. So here, there is only 1 polyatomic ion, it's the phosphate, and there is 2 on the right side and only 1 on the left side. So we want to make it 2 phosphate on the left side, and so we will add a coefficient on the left, and it will go in front of the Na3PO4 because that's the compound that contains the phosphate. So that's balancing the phosphate. Because the phosphate on the right side is with magnesium, and it's a complicated formula, we don't want to have to put a coefficient in front of this. So let's balance the magnesium now. And we have 3 magnesium on the right, 1 on the left. So let's make it 3 on both sides by multiplying by 3 on the left side. And that coefficient 3 will have to go in front of MgCl2 to make it 3 magnesium on the left. Then you need to recount your number of ions and balance what is not balanced. Because those coefficients we added on the left now, they will change the number of sodium. You see that now we have 2 Na3PO4, which means 2 times 3 Na, it's going to be 6 Na now. 6 Na, 6 Na on the left. And if we look at MgCl2, there is a 3 in front, which means it will change the number of Cl. And 3 times 2, it's going to be 6 Cl on the left side. So we have 6 Na on the left side and 1 on the right side. So let's make it 6 by multiplying by 6 on the right. And that 6 will be coefficient 6 in front of NaCl. And this way it will also balance the chloride, because you see that chloride has a 6 chloride on the left. And by having the 6 in front of NaCl, we also have 6 chloride on the right. And so by just adding that 6, it looks like it's all balanced. Let's check the final equation to make sure it's balanced. So let's count the sodium ions. Sodium, we have 3 sodium on the 3 sodiums in Na3PO4 times 2, it's 6 on the left. And 6 NaCl on the right, that's 6 sodium. PO4, we have 2 PO4 on the left and 2 PO4 on the right. Magnesium, we have 3 magnesium on the left and 3 magnesium on the right. And then chloride, we have 3 times 2, 6 chloride on the left and 6 chloride on the right. So it is balanced, and that's the final answer for this equation. So let's practice with this example. Acetic acid reacts with the metal aluminum to make aqueous aluminum acetate and gaseous hydrogen. So what you will learn in chapter 9 is that acids are always aqueous, and so HC2H3O2 is the acetic acid and it's aqueous. So you see AQ in parentheses to indicate it's an aqueous solution. Again, aqueous here means it's dissolved in water. Aqueous refers to the fact that the solvent is water. Aluminum, when we talk about the aluminum metal, then the symbol is just Al as a solid. And then on the right side, we have the aluminum acetate and the hydrogen gas. So the hydrogen gas is, the hydrogen is one of those 7 diatomic molecules that come up as gases in nature and diatomic molecules. The list is H2, N2, O2, so N2, O2, F2, Cl2, Br2, and I2 are all gases and diatomic molecules in nature. So when we are ready to balance this, we want to treat the polyatomic ion acetate as a unit. You want to count the ions. And so you will keep the acetate as one ion. So the formula will be C2H3O2, and you want to count, you know, this unit. Do not count individual atoms. It would be a waste of time and energy. So let's count aluminum. Aluminum, we have one on the left and one on the right. Then the acetate ion, we have one on the left in HC2H3O2. So here you're only counting after the first H, and it's one. In the right, you have 3 acetate per aluminum. Now let's count hydrogen, because you see that on the left side, the hydrogen is associated with the acetate ion, and so there is 1 hydrogen there. And on the right side, there is 2 hydrogens in the diatomic molecule H2. So we need to balance the acetate and the hydrogen. And you always want to start with the polyatomic ions. And so here we have 3 acetates on the right, only 1 on the left. So let's make it 3 on the left by multiplying by 3. And that coefficient 3 will show up in front of the acetic acid. By doing this, we are changing the number of hydrogens, because the 3 here belongs to the whole formula for the acetic acid, and it contains the acetate ion and an hydrogen. So this changes the number of hydrogens to 3 on the left. And so now we have 3 hydrogens on the left, 2 on the right, and whatever we will put in front of the H2 molecule there will have to be multiplied by 2, because there is 2 hydrogens per formula. And we have 3 hydrogens on the left. So by multiplying by 1.5, we will make it 3 on the right. Remember that we do not want to have coefficients that have decimal places. So we will need to multiply all coefficients by 2 to get rid of that 1.5. So let's multiply all coefficients by 2. And so in front of aluminum, it's going to be a 2. In front of the acetic acid, it's 3 times 2 is 6. In front of the aluminum acetate, it's going to be 2. And then the 1.5 times 2 is going to be 3 in front of H2. So let's verify that this is balanced by counting the atoms again. So on the left side, we have 2 aluminums and 2 aluminums on the right. Acetate, we have 6 acetate on the left and 6 acetate on the right, because we do 2 times 3 is 6 for acetate. The hydrogen, we have 6 hydrogen on the left, and on the right we have 3 times 2, 6 hydrogens on the right from H2. And so this is balanced. So let's practice more with this double replacement reaction, where we have bismuth nitrate, and NaOH gives bismuth hydroxide and NaNO3. So Bi is the bismuth. So let's count the ions. These are all ionic compounds, so we will count the ions, and we will keep polyatomic ions as one unit and count them as one, like if they were one thing. So bismuth, in those compounds, it's bismuth 3+. So there is one bismuth 3+ in the left and one in the right. Next, it's the nitrate polyatomic ion, NO3 - 1. There is 3 nitrates on the left in the bismuth nitrate, and only 1 on the right in the sodium nitrate. Next, let's count the sodium. We have 1 sodium on the left, 1 sodium on the right. And then the hydroxide ion, OH- is the hydroxide ion. And there is 1 on the left associated with the sodium and 3 on the right associated with the bismuth. So when you have polyatomic ions, like here you have 2, the NO3 -1 and the OH -1. So you want to start with them. So let's start with nitrate. We have 3 nitrates on the left, 1 nitrate on the right. So let's make it 3 on both sides by multiplying by 3 on the right. And that coefficient 3 will have to go in front of NaNO3 because that's the compound that contains the nitrate. That balances the nitrate. Let's balance the hydroxide. We have 1 hydroxide on the left, 3 on the right. So let's make it 3 on both sides by multiplying by 3. And that coefficient 3 will go in front of NaOH to make it 3 hydroxide ions on the left. By doing this, we have changed the count of sodium. You see here that now we have 3 sodium on the left and 3 sodiums on the right. Right? This balances the sodium. The nitrates are balanced. We balance them. The bismuth are still balanced. And the hydroxide ions are balanced. So it looks like with those 2 coefficients, it's already balanced.